Okay, this video is for my DCAC class. The first week we're supposed to talk about scientific notation, engineering notation, the need for scientific notation, and then entering scientific notation in Scilab and entering engineering notation in Scilab, which is really going to be the same thing. First of all, scientific notation. Basically, scientific notation is a way to represent big numbers. For instance, it is 93 million miles between the Earth and the Sun. That's a big number. That would be 8 digits. If your calculator can only handle 6, then you cannot do anything with 93 million miles. You could also have a number that's even bigger. For instance, the number of electrons or number of molecules in a mole, which is a chemistry term. So that would have 21 zeros there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21. I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. Yep, 23 zeros. So that is how many molecules is in a mole. It's a chemistry term, but extremely large numbers. If we want to talk about the amount of charge on an electron, it is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There. Something along that line as far as a number. It's a very, very tiny quality. Again, chemistry, physics, you get into these huge, huge numbers or very, very small numbers, and we need a convenient way to represent them. Getting back more into the course, and also to tie into engineering notation in the future, let's say I have a resistor that is 470,000 ohms. So, how can I represent this in scientific notation? Well, anytime you write out a number, you can always multiply that number times 1. So, if I multiply 93 million by 1, then most of the times you wouldn't write times 1. But what I want to do is I want to put 1 in a different form. 10 to the 0 power. Okay? In your laws of exponents, you learn quickly that if you take anything and you raise it to the 0 power, it's the same as writing a 1. So, to get to scientific notation, the first thing we're going to do is we're going to go in there and we're going to say, oh, well, I can do that for any number out there. So, I will just do it. Maybe copy and paste might be faster. Let's see what we get here. Control C, Control V. So for any number out there, you can do this. Okay? Not in scientific notation yet, but I'm getting into the form of it. Now, what we need to see is that our decimal in in any number is at the far right end of the last 0. For that one, and then if it's a very small number, then we're going, our decimal is all the way to the left, and it becomes a very small number. So, but I can always put a decimal in any number, and I'll add another one here that's kind of small, but not too crazy small. So let's do 0.005. There we go. So that's got a decimal 2 times, and I can always multiply it by 1. So now I got 5 numbers here. All of them, all I did was go in and multiply them by 1. That does not change the value of them. Now the key to scientific notation is to move your decimal place to where you only have one number or one numerical value to the left of the decimal. Has to be between 1 and 9. A 0 doesn't count. You would shift it so that you have something other than a 0, but you would not have 2 digits to the left. You would only have 1. So in this case, I need to shift this decimal 1, 2, 3, 4, 5, 6, 7 places. And then I would be 9.3. Now, 9.3 as compared to 93 million is much, much smaller. By 7, I moved my decimal 7 places to get there, which means this 0 here on this 10 has to get bigger. And I'm going to Control V and then go in here and just edit this. There we go. Okay. So, scientific notation, that's what you're doing. If you make this number smaller, you're making your decimal bigger. They are equal. It's 2 different ways to represent the same number. Now, if I had a problem, and we will work a problem later with a number in this form, then my calculator could certainly do it in pieces at the very minimum, and it might be able to handle the whole thing. If my calculator would not take this many digits, then I can't do the problem. Okay? Same thing based on scale. This one, I got to move this. If I counted right, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23. So that would be equal to 6.02 times, do that, and then 23. Hot dog. Okay. Again, equal. This number went from huge, so many zeros it just blows the mind, down to 6.02. Excuse me. So this 0 had to go up by the same amount of places that I moved the decimal. It's that easy to get into scientific notation. I'm going to skip this one for the time being, go to this 470,000. Same process, 4.7 times, add that. How many places do I have to shift it? 1, 2, 3, 4, 5. So, to the 5th. Okay. 1, 2, 3, 4, 5. Yep. Alright. Again, smaller, this got bigger. What do you think happens when I have to go and make this number bigger? Because 0.00016 is a very small number. Matter of fact, we should start with this one down here. 0.005 is a very small number. I want to make it big. I want to make that a 5. So what has to happen to my tens? I have to make it bigger, and I have to move this decimal 1, 2, 3 places. So instead of a 0 behind the 10, it would be a 3. And instead of it being a positive 3, it's a negative 3 because of the direction I'm moving here. And we got to make that all subscript. So 0.005 times 10 to the 0, which is 1, is really 5 times 10 to the minus third. Okay? Can I apply that up here? Why, absolutely. You probably have done it already, right? 1.6. And if I did it right, I should be at, that's what I meant to anyway. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19. 10 to the minus 19. Again, same number. Equal signs mean both sides are the same. Different ways to represent it. A more simple way to represent it. That is scientific notation. That is proper scientific notation. So these are proper. An improper scientific notation would have the same form as scientific notation, but it may have, I can shift it a little bit. And we need to understand this concept in terms of going into engineering notation, because we're going to want a certain power of 10 in engineering notation, whereas in scientific notation we want a specific power of 10. So an improper scientific notation, what if I took this this number right here and I copied it down, Control C, and I Control V'd it, and I want to make it improper? I can make it anything I want. What if I make this number bigger? What has to happen here? Make it smaller. What if I make it smaller? I can make it bigger. So if I make the 4.7 smaller, I can go 0.47, which is smaller, which means my 10's power has to do what? My 10's power has to get bigger. Whoops. And I have to make sure my superscripts are right. So, that got smaller, that got bigger. Can I go the other way? Absolutely. Absolutely. Knock off the subscript. Put in an equal sign. What if I wanted to make it 470? 470. So here I'm at 4.7. I want to shift it 2 places, make it 100 times bigger, so this has to go down to times 10 to the 3. Superscript. Well, wait a minute, Jim, why didn't you do 4? Well, I can do 4 if I want to. You can do it. You can do whatever form you want it. Some of them are going to be a little more appropriate than others, but I could say 47 times 10 to the, what would that be? 1, 2, 3, 4, 10 to the 4th. Everything on this row is equal. Different ways to represent it. Where I get an engineering notation is I want to get in powers of 3. So 10 to the 3rd. So if I do 10 to the 3rd, take off my subscript. This is going to be my kilo or my K representation. What about if I do 10 to the 6? Well, mega M. Alright, so in engineering notation, I want my 10's powers to be in 3s. And then kilo and mega are the 2 most common. There's also a 9, which would be giga. Okay, and I can go the other way. Can I go 10 minus 3? Oh, absolutely. 10 minus 3, and that would be M. 10 minus 6, minus 6. Micro. Clean these up. 10 minus 3 is milli. 10 to the minus 6 is micro. Well, as you can see, we are using the first letter as the symbol, K, M, or G. If we're going above 0 or capital, generally, I have seen K as lowercase. If we're going below 0, we're going to be lowercase. Well, since milli and micro start with the same one, they had to use something different. They actually use a Greek letter called mu, but a lowercase u will often work if you're doing word processing. Okay, 10 to the minus 9. Nano, and that would be a lowercase n. So fix that. There you go. Engineering notation. Those are the most common 6. Obviously, there's a 12, a minus 12, and a plus 12. There's a 15. There's an 18. Goes on. You can look them up in a table. Tables are readily available. What we're doing with engineering notation is we want to take something like this. When we see this 10 to the 6, we can say, okay, what do we want to use here? So I'm going to borrow some of this stuff from above. First of all, I'm going to borrow this. Control C. Bring it down. Whoops. Had a little white space. Can I get this to a convenient metric prefix? I absolutely can. I happen to know that 93, what I intended was that it is in miles. So this is how many miles it is. Well, if I change my unit notation, if I change the number, I'm still not changing the unit, so I'm still in miles. So what I'm looking for now is, can I put this in a form that fits the engineering notation table? And I absolutely can. I can make it 6. So if this gets bigger, what has to happen here? I mean, this would go from a 7 to a 6, would make it smaller. So 9.3 has to go to 93. 93 times 10 to the 6. M-I-L-E-S. Superscript. Beautiful. Okay. The nice thing about engineering notation is I don't have to write this times 10 to the 6 anymore. I can just write 93 M for mega miles. So now what I've got is something here that is completely equal all the way across the board. 93 times 10 to the 0 miles is the same as 9.3 times 10 to the 7th miles, which is equal to 9.3 times 10 to the, or 93 times 10 to the 6 miles, which is equal to 93 mega miles. And I picked this one for the same reason. Oh no, I'm looking for a convenient engineering notation. Well, I already got it. It's right there, and it's right there. So if I look at those two, and I go in here and I look at my metric prefixes, I could represent this as 0.47 micro some unit. I'm going to make it ohms. So that's ohms. That's ohms. 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 We don't want it superscripted. Ohms. Ohms. Okay? Again, everything's equal. This ohms is equal to 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 this ohms. It's just a different way of representing it. So I did the 0.047 times 10 to the 6. Excuse me, it was meg. Replace 10 to the 6, so I got to use the capital M. I'm thinking micro for some reason, probably because of the one above it. Or, no, I don't know why I got off on that tangent. But anyway, there we go. And can I make that the same as K? Yeah, absolutely. I can go up here and look at 470, 10 to the 3, and say, oh, that's also equal to 470 K ohms. Okay? Now, what's the preference? Well, the first thing to do, and the important thing to do, is to get things right. Get the right value, and then work on the representation in order to make it more pleasing. Typically, people are not going to talk about 0.047 megohms, although technically it's correct. More often than not, you'll be talking about 470 k ohms. You could talk about 470,000 ohms. You could talk about 4.7 times 10 to the 5th ohms. Any of those is technically correct. Then it gets into a little bit of semantics about, well, what do I want to see? For ohms in a DC-AC class, most of the time you're going to be dealing with k ohms. Okay? If we're dealing in k ohms, then we will need to be dealing in amps, and that was why this one was chosen. So I'll bring this down, and I say that, ooh, this is an amp. This is a unit of current. So this is an amp, a unit of current. So what can I do with that? Well, I can continue changing them. Can I go smaller? Can I make my 5 bigger and my 10's power smaller? I absolutely can. I can add 3 zeros to the 5 times 10, and now it's minus 6 amps. And what we're doing with engineering notation is we are trying to get it to where our 10's power matches one of the prefixes, and then we just substitute. So then I can substitute. So 5 times 10 to the minus 3, well, 10 to the minus 3 is milli, so I could say this is 5 milliamps. And if you want to be crazy about it, you could say it's 5 microamps. That's probably where I was thinking of the micro. I was thinking a little bit ahead. So again, all this is equal. Different ways to represent it. Normally, as people, we like to see 1 or 2 numbers. So if we can get it to a convenient, or maybe 3 in the instance of this 470 k ohms, 3, 4, we get over 1,000, 10,000, it starts being a little mind-boggling for us. So we're trying to, so now we have a way to represent numbers and units in terms of something that is something we can sort of see. Now, why do I need scientific notation? Well, if I go back up here and I wanted to take this number and divide it by that number, then, or even multiply it by that number, you can't do it on a calculator. So I would need to be able to do that on a calculator. So I have to at some point do it. Keeping track of all these zeros, if you're going to multiply or you're going to divide or whatever, you've got to make sure you follow all the rules, and you just made the problem much bigger. If I can break it down into these 2 pieces, if I can break it down into numbers that look like this 6.02 times 10 to the 23rd, and it's 1.6 times 10 to the 19th, then what I wind up doing is I wind up doing my multiplying or addition, or well, multiplying or dividing of these 2 numbers, which I can do on a calculator, and then I can use my exponent rules for figuring out the 10's power. So it's pretty simple. So let's just multiply these 2. I'm going to multiply 6.02 times 10 to the 23rd times 1.6 times 10 minus 19. And go in there and correct my exponents. Okay, I can do that. What this practically means is I need to multiply the 6.02 times the 1.6, which I can do, and then I'm going to multiply it by 10 to the 23rd and times 10 to the minus 19. So I superscript it and we're good to go. 6.02 times 1.6 is one thing, 10 to the 23rd times 10 to the minus 19. If you read up on your rules of exponents, you got like bases raised to an exponent, you multiply them together, you simply add the exponents. So I'm going to get a 10 to the 4th here. So I can do this one without a calculator. This is just adding and subtracting. So I'm reducing that big number to something easy. 6.02 times 1.6, oh, I don't know what that is off the top of my head. So did I close Scilab? Looks like I did. Yes, I did. There we go. So I closed Scilab, so I'm opening it back up here. I got to multiply 6.02 times 1.6, so 6.02 times, which is shift 8, 1.6 gives me 9.632. So if I come down here, it's 9.632 times 10 to the 4th. 6.02 times 1.6. There we go. Yep. Backspace and delete. There you go. Looks better. So I can do this now. With the usage of scientific notation, I can bring any big number I want to down to something that I can manipulate on any calculator. Which brings us into entering the scientific notation in Scilab. I can't obviously do that many zeros. Scilab might, but might have a hard time with it. How do I do that? Well, on most calculators there's a shortcut. This times 10 to the minus 19 and times 10 to the 23, there's some kind of shortcut to entering it, and you want to figure out what the shortcut is for your calculator. Usually it's an EE key or something like that. In Scilab it's pretty simple. I can do this problem directly. I can say 6.02, and the way I represent my exponent is E23. So instead of times 10 to the 23rd, I'm substituting that with an E. And then I'm writing down the value or the power of the 10. And then I'm going to multiply that times my other number, which is 1.6 E. And remember, it's a negative exponent, minus 19. So that would be how I would enter that into Scilab, which it calculates it directly. Now notice, it gives me the non-scientific value of it. So if I go back to this point and I want to make it 10 to the 0, what would that look like? I got to move this 4 places to get this times 10 to the 0. So 1, 2, 3, 4. So it would look like 96.32 times 10 to the 0. And most places don't write out the 10 to the 0, but it's before entering it. And as you can see, that's exactly what Scilab gave me. Okay, so if I want to enter my scientific notation in Scilab, this is how I do it. I should be able to come up and copy and paste here. That's what it would look like entered in Scilab. That's not what you want to put on your paper. You want to make sure it's in the right form. Entering engineering units in Scilab, what you have to do is, let's say something like 20 milliamps times 15k ohms. Let's say I want to do a problem like that. Well, we know from the table up above that when I see the m, I'm really talking 20 times 10 to the minus 3, or 10 to the minus 3. When I see the k, I'm talking about 10 to the 3. So if I wanted to do this, I could go ahead and change it, scientific notation. So this would be 20 times 10 minus 3. And then I'm going to hit the times. 15 times 10 to the third. And what, pray tell, does that equal? Well, again, you can almost do this in your head. 10 to the third times 10 to the minus third times 10 to the third is going to wind up being 10 to the 0, which is a 1. So we can do this in parts. 10 to the 0. And we're left with 20 times 15. What is 15 times 20? Well, that would be 300, right? 300 times 10 to the 0. Which is equal to what? 300. Now, how would I do that in Scilab? Well, you have to kind of know what your metric prefixes are. So when I see 20 milliamps, I'm going to do 20e minus 3. I'm taking this m, substituting in my exponent minus 3. I'm going to multiply that times 15, e to the third. Again, I'm changing it just like I did here as an interim step into Scilab. I hit enter. It tells me it's 300. So this is how I would enter. You got to know your metric prefixes enough to change them back and forth. Okay, this should be enough of a primer to get you through the worksheet, if you will. And we are going to be using metric prefixes the entire semester. You're going to get used to them, and so you'll get plenty of practice. Scientific notation is sort of the basis for it, so they go hand in hand. But that is where we're at. Y'all have a great day.